Hello and good morning. Okay, so today we will talk about NP completeness, a concept that I think every CS student should know. And then on Friday, I will talk about the solution to our two homeworks, homework 5 and homework 6. Okay, so let's start. Okay, and the slides of this class is accessible through the link that is attached in this YouTube video, or you can go to my webpage and then search for earlier years of the algorithm course. So first of all, we will talk about what is meant by a problem is an NP problem, and then we will describe how to check if a problem is an NP problem. And then I will mention something called the Cook-Levin theorem. And then the Cook-Levin theorem actually defines a certain problem and then show that this problem is the most difficult problem in NP. So we are going to classify the problems into different groups, but then for certain group of problems, we call them NP problem. And then among all the NP problems, some of them are very, very hard. You can say that it is the hardest of all the NP problems. These problems, we will call them NP complete problems. And then we will also mention a technique called problem reduction. And then this problem reduction technique allows us to show that more and more problems are also very hard as the hardest problem in NP. So they are also NP complete problems. Okay, so first of all, we have the concept of a decision problem. So in a decision problem, our concern is whether the problem has a solution or not. So the answer for this kind of problem is either a yes or a no as the answer. So let's take a look at these two examples. So the first one is, say, a certain friend, Peter, he gives us a map and then he asks us if there is a path from A to B whose length is at most 100 units. So this is a problem. And then the answer for this one is either yes or no. Yes, when there is a path of length at most 100 units, and no, it means that for no matter what kind of path that we can find between A and B, the length is at least or greater than 100. Okay, so this is a yes no type problem. The other one is, let's say your sister gives you a number, and then this number in decimal, it is a very, very interesting number. It has 19 ones together, and then she asks you if this number is a prime or not. So in such a case, this is also a yes no type of question. So the answer is either yes if it is a prime and no if it is not a prime. Okay, so some of these decision problems can be solved efficiently using polynomial time to the size of the input. If this is the case, then we say that the problem is a P problem. So P means that it is a polynomial time solvable problems. So in the first example, so Peter gives a map and then asks us whether there is a path of A and B at most 100. We can apply the Dijkstra algorithm or the shortest path to find the shortest path between A and B, and then based on the solution, if it is less than or equal to 100, then we answer yes, and then if it is not, then we answer no. And because Dijkstra's algorithm runs in polynomial time, so we will see that Peter's problem is a polynomial time solvable problem, so it is also in P. The second problem gives us a very large number, let's say a large number n, and then we want to find whether this n is a prime number or not. Of course, as mentioned very early at the beginning of this course, we can have an algorithm that checks whether n minus 1, n minus 2, and so on and so forth, up to 2, whether any of the numbers can divide properly the number n. But then this algorithm runs in exponential time in terms of the size of the input, so it is not a polynomial time algorithm. So the question here is that given the number n, is it possible to design a polynomial time algorithm to solve this problem. If there is a certain polynomial time algorithm that can solve this problem, then it is a polynomial time solvable problem. If it is not, then it's not. Okay. It turns out that for this particular problem, it is a polynomial time solvable problem as well. So your sister's problem is also in P. Okay. So Peter's problem is in P. Okay. Now, among the problems that we have, not apart, I should say, apart from the problems that we have just discussed that they are polynomial time solvable, computer scientists are also interested in another type of problem. So this problem is called polynomial time verifiable problem. So what does that mean? So it is a decision problem such that if the answer is yes, then I can give you a proof, and then you can look at the proof and check that it is really a yes solution. Okay, so if the proof is short enough, and also you can check the proof and use the proof to verify that it is really a yes as its solution, then this kind of problem is interesting for computer scientists. Okay, so for instance, in Peter's problem, that we want to check whether there is a path between A and B with length at most 100 units, then this is also a polynomial time checkable or polynomial time verifiable problem. It is because whenever there is a yes solution for this problem, then that means that we can really find a certain path between A and B with length at most 100. And what we really need to do here is we can tell the user what are the vertices along the path from A to B. So the user can really easily check whether the vertices that you give really forms a path that connects A to B, and then check whether the total length of this path is less than or equal to 100. Is that okay? So for this problem, this is also a polynomial time verifiable problem. And how about this one? So if your sister gives you a number, so if I have a number n, I want to check whether n is prime or not, then suddenly this problem is interesting. So if it is a prime, then there may not be any easy proof, okay? But if it's not a prime, then it is there is an easy proof. I just tell you one of the factor of this n, and then you can check whether n can be properly divided by this factor. So this type of problem, it is the opposite is polynomial time verifiable. We are also interesting. Okay, but it turns out that from the from the what from the theory side, whenever a problem is polynomial time solvable, then it must be polynomial time verifiable. Wow, that's kind of interesting, right? Why? It is because the proof that we can give the user is we just tell the user how our polynomial time algorithm can solve the problem. We tell the user what are the execution steps in our algorithm, one step by another, so that the user can check whether each step is correctly performed, and the total length that in these execution steps must be polynomial because it is polynomial time solvable, right? So the user takes polynomial time to check whether each step is executed correctly, and then after that can verify that it is really a yes solution. Okay, so here, this is a recap of what I've just mentioned. So another example here is, suppose that I have a graph, and then I want to check whether the graph contains a Hamiltonian path. So recall that what is meant by a Hamiltonian path. A Hamiltonian path is a path that connects every vertex together but then each vertex can appear in the graph in this path at most once. Okay, so in that case, at most once, and then it has to connect. That means that each vertex appears on this path exactly once. So is there a way that we travel from vertex to the other one by one, such that after the traversal, we can visit all the vertex exactly once? Okay, then in that case, this is called a Hamiltonian path. And then given a graph G, we want to determine whether the graph has a Hamiltonian path. Now, this problem is a polynomial time checkable or polynomial time verifiable problem. It is because whenever the solution is yes, whenever there is a Hamiltonian path, then there is a very easy way to give a proof that the user can check whether it is true. So the proof is I just list out all the vertices along the Hamiltonian path. So the user can check step by step whether it is really an edge in the graph, and whether this is altogether a path, and then in the end check whether each vertex really appears exactly once. So everything can be done in polynomial time. Okay, so this is the first example, Hamiltonian path problem. The second example is just mentioned. So I have an integer x. Can we check whether x is a composite number? Okay, if the answer is yes, which means that x is a composite number, then the proof is I tell you one of the factor of x, non-trivial factor. It's not one, it's not x, but some number that divides x properly, and it is between 1 and x, non-inclusive. Okay, then in that case, when we receive a number, we can check whether this number properly divides x easily in polynomial time. So in that case, this problem checking an integer whether it is composite is also polynomial time verifiable. So recall that when we want to have a check, we just check for the yes cases. If the answer for the problem is no, then we don't provide the proof. But if the answer is yes, then we will need to get the proof so that the user can check it very quickly. And then another one is, suppose that I have a collection of numbers. Can we divide this collection of numbers into two groups such that the sum of each group turns out to be equal to the sum of the other group? Okay, so the sum of these groups are the same. So for instance, suppose that I have the set of numbers 1, 2, 3, 4, something like this. Okay, this is a very simple collection. Okay, 1, 2, 3, 4. So can we divide the groups of numbers into two groups, okay, subgroups, so that the sum will be in each group is going to be the same as the sum of the other one. So I can 1, 2, 3, 4. I can make 1, 4 into one group, and then 2, 3 into the other, so that the sum of each group is equal to 5. And then for this one is yes. Okay. Now for this problem, then it is also polynomial time verifiable, because if there is really a way to divide the groups into two parts, then I just tell you what are the numbers in the first part and what are the numbers in the second part. The user can check whether we are really dividing the numbers into two parts so that each number appears once, and then to check whether the sum of the first group is equal to the sum of the second group. Okay, so all things can be done in polynomial time. So if this is the case, then this is called the polynomial time verifiable problem. Okay. Okay, so here what is meant by the class of NP? So NP here means that it is the collection of all the polynomial time verifiable problems. Okay, so why is it related to P? Because the checking part is P, right? And then what is N? N doesn't mean not. Okay, N here means that it is non-deterministic guessing power. So whenever we define an algorithm, usually we our algorithm is called a deterministic algorithm because it will carry out our instructions one by one. Every time it does the same thing on the same input, right? But then imagine that our computer is now uh, given some kind of guessing power. So somehow our computer can guess a solution, can guess a proof for a problem to be a yes problem. Okay, so if we have a problem, right? So in this problem, so we will try to guess whether it is the answer is yes. So to guess whether its answer is yes, then we will also need to guess what is a short proof for this one. So somehow, if we guess correctly, then the execution of the checking parts can be done in polynomial time. So if a problem can be solved in this case using polynomial time, then it is an NP problem. So the guessing part is the non-deterministic power of our computer. So we can imagine that this computer can run different guesses simultaneously, like in parallel. But as long as one of the guess is correct, then we can verify the problem to be a yes case. Then in that case, this type of problem is called a NP problem. So in the previous page, all these problems, they are NP problems. So here, for the first type of problem, we get the Hamiltonian path. For the second problem, we guess the vector. And then for the third problem, we guess how we divide the two groups. Divide the group, the collection into two groups. So far, if you are okay, so let me double check if you are okay with what I'm saying. So far so good. Okay. So somehow, if there is a way that we can guess the proof and then after that check the proof, so guessing part doesn't take time. So imagine you can guess very smartly that it is very smartly whenever it is a yes answer, we can guess very smartly what kind of proof that can tell us that it is a yes. Then in that case, we just need to focus on the checking part, whether it can be done in polynomial time. So all these problems, we call them NP problems. Okay, so recall, yeah, this is important. The N part here means it is the guessing power. It has polynomial time checking with the super smart guessing power. Okay. Now here, so we know that. So we have just mentioned briefly about this. So we can claim that every problem in P must be a problem in NP. So if a problem can be polynomial time solvable, it must be polynomial time verifiable. The reason is that we can guess the execution. So it is a polynomial time solvable problem. That means that it has an algorithm plus the execution. So the execution part itself is not long. It's very short. It is only of polynomial length. So we guess the execution, and then the execution together with the algorithm will provide us a proof that the answer of the problem is really yes. Okay. So this is the execution steps of the algorithm. It's a so-called proof for this to be a yes case. So what we know here is that using set theory notation, P is a collection of problems, NP is a collection of problems, but then we see that every problem of P must be a problem in NP, so that P is a subset of NP. Is that okay? But somehow, okay, it looks like there are some part of the NP problems it is really hard. So all the problems of P are polynomial time solvable, but somehow some problems in NP, they are really hard. So nobody knows how to solve them in polynomial time yet. So for instance, checking whether a graph has a Hamiltonian path. So this problem after so many years, nobody knows whether we have a polynomial time algorithm to solve this. Only we know that it is polynomial time verifiable. Okay, so at this moment, there seems to be some problem, but we are not sure. There seems to be some problem that is located in NP, but they do not have a polynomial time algorithm. So if this is true, then that means that P and NP are not the same. So there are some problems that is in NP, but not in P. But somehow, this whether P and NP are the same or they are not the same is still an open problem. So nobody can give the answer whether P is equal to NP or not. So this is a problem that worth 1 million US dollar. If you can somehow provide the proof whether in the positive side that P is equal to NP or in the negative side where that P is not equal to NP, then you will, if the proof is correct, then you will get 1 million US dollar. Okay, so this is the current status. Okay, so as mentioned before, we know that if a problem is in P, then it must be in NP. Yeah, P is a subset of NP. But then if a problem is in NP, then it may be in P or not. Okay. Now, what we are going to talk about next is we are going to look at the problem, a special problem called SAT that is studied by two persons independently. So one is Stephen Cook from Canada, and the other is Leonid Levin from Russia. So they both studied the same problem independently, and then they find it very interesting. Okay, this problem some kind represents the hardest problem in NP. So what does they find out? So they find out that this problem SAT, so we will define what is SAT soon. So they say that if this problem SAT is in P, then every problem in NP are also in P. So SAT is, that means that, so that is if SAT is in P, then every problem in NP is also in P. So then that means that P is equal to NP. So Cook-Levin studies this problem and have this result. This result is proven to be correct. But then, if this is true, then why don't Cook and Levin get the $1 million from the CMI? Okay, it is because they are not really showing whether P is equal to NP or not. They are showing a conditional statement. So they just mentioned that if this is true, then this is true. But at this moment, we don't know whether this part is true or not true. Okay, if this is really true, then they prove that P is equal to NP. But if this is not true, of course, they also show that P is not equal to NP because SAT is not in P, then SAT is in NP. So there is a problem that is only in NP but not in P. But the question here is that whether the condition here, SAT is in P or not, we do not know. Okay, so Cook and Levin cannot get this 1 million US dollar because their argument here is conditional. But somehow we can see that this SAT turns out to be the hardest problem in the NP groups of problems. Yeah, because if this can be solved easily, then everything can be solved easily. So this is like the hardest problem. And in computer scientist language, then we call this the hardest NP problem, and then we call this the NP complete problem. Okay, so the complete here means that it is completely hard, completely difficult. So NP complete means that it is the most difficult problem in NP. So what does SAT problem looks like? Okay, so the SAT problem looks like the following. So we are given a certain formula. So you can say it is like an equation or something like this. So the formula, let's say F, looks like this. So there are some variables inside. So we have variables x, y, and z. Okay, this is a logical formula, a Boolean formula, so that we have this or notation. This is the not, this is the and. Okay, so we have this formula, and we want to find out whether there is a way to set x, y, z into true or false, so that the total formula itself here becomes true. If there is a way to do so, then this formula is called satisfiable. If it is not for all the possible way to assign true false into this xyz, there is no way to make it true, then it is called an unsatisfiable formula. So the SAT problem is, I have a formula, a Boolean formula. I want to check whether it is satisfiable or not. So for instance, in this particular example, let's say we set x to be false, y to be true, and z to be true. So false, true, true, and let's see what will happen. If x is false, then this is the negation of x. This will become true. Now, because y is true, then true or something will become true. So this is also true. And if z is true, then this is also true. So false, true, true. X false, y true, z true. We'll make this true. We'll make this true, and we'll also make this true. And in the end, the formula will be true and true and true in this case. So it is true. So in such a case, then this formula is satisfiable. But in general, the formula could be very complicated. It may involve a lot of variables. It may have a lot of this and or not things inside. And determining whether there is a certain way to assign true false to the variables and make the whole thing true will become difficult. So far this problem is known to be a hard problem. Okay. Okay, so now Cook-Levin. So Cook-Levin proves that this SAT problem is really hard. So they prove this statement. So this is now called the Cook-Levin theorem. Okay, Cook-Levin spent a lot of time to get a proof that, or a very tedious proof actually, to show that this SAT problem is the hardest problem in NP. But after that, suddenly, over the years since Cook and Levin, we now can show that millions, and not millions, maybe thousands or 10,000s of problems now, that they are all NP complete as well. So why suddenly that computer scientists are now cleverer than Cook and Levin, and then they can show that these many new problems are also NP complete? Okay, because they have now got a new technique called problem reduction. Okay, so problem reduction is the technique. So the reduction word here, you can replace it by transformation. So it is a problem transformation technique. So this is a technique that we can transform a problem into another problem in the following way. Okay, so the idea here is that suppose that we have two problems, one of them called A and the other called B. Somehow we know that A is very difficult. But then we can also show that if we can solve B, then we can solve A. Then can we conclude anything here? So A is very difficult, right? But then we can solve B, then we can solve A as well. So what does that mean? So whenever we can solve B, that means that A can also be solved. So the problem of B must now be harder than the problem of A, right? Yeah, because whenever we can solve B, we must be able to solve A. So it doesn't can solve A, we can solve B, right? So imagine, let's say A is solving finding roots. So this is just about problems. Okay, so let's say A is finding the roots of a quadratic equation, something like x squared minus 3x plus 2 is equal to 0. So what are the possible values of x here? So this is a quadratic equation. And then let's say B is the problem of solving a cubic equation. So for instance, suppose that I have x cubed minus 1 is equal to 0. So what are the possible values of x? And then we can see that if some genius can always solve a cubic equation, then we can ask the same guy to solve quadratic equation for us. It is because when we are given a quadratic equation, let's say x squared minus 3x plus 2 is equal to 0, we can easily turn it into a cubic equation by multiplying x to it. So it becomes x cubed minus 3x squared plus 2x is equal to 0. Is that okay? And then we proceed to ask the smart guy, to solve the cubic equation for us, so that we get the roots, and then two of the roots will be the solution of the original problem, and then one of the root is 0. So apart from one of the root, which is 0, the remaining two roots will be the original roots of the quadratic equation. So here we can see what? Whenever we can solve cubic equation, we can solve quadratic equation. Then what does that mean? It means that cubic equation, the problem of solving cubic equation must be harder than, or at least the same hard as the original problem of solving quadratic equation. Okay? So this is the idea of connecting the difficulty of two problems. So if B can be solved whenever, if A can be solved whenever B can be solved, then A is easier and B is harder. Okay, now we have another problem reduction. So for instance, A is finding the median of a set of numbers, but then B is sorting. So that we know that if we know how to sort, we can find the median, right? So what do we know? We know that sorting is harder, or at least as hard as finding the median. And similarly, we have topological sort and DFS. So if we know how to solve DFS, then we can solve and perform topological sort. So topological sort is easier, and DFS is as hard as the topological sort. Okay, now let us consider this idea. Okay, so suppose that A somehow is a known NP complete problem, and B is another problem in NP. Suppose we can show the following two things. Okay, the first one is we can transform the problem in A into a problem of B in polynomial time. And then suppose that we can do so. Okay. And then the second part is, if we can answer B, then we must be able to answer A. Then in that case, we can conclude that B is NP complete. The reason is that, so first of all, the first part actually established the fact that A is easier and B is harder, right? So, or B is at least as hard as A. But then there could be many hard problems. So, but then B is also within NP, and A is already the hardest problem in NP. So it implies that B cannot be really harder than A because A is already the hardest. So in that case, it implies that B is also one of the hardest problem in NP, so that B is also NP complete. But then here, we emphasize that the transformation has to be taken into using polynomial time, because it guarantees that whenever B is polynomial time solvable, so will A, because we can first turn A into B in polynomial time and solve B, and use the solution of this one to imply the solution of A. Okay, so this polynomial time is important. If we are using exponential time, it doesn't make any conclusion. Yeah, because we can always change a problem into an exponential time, into some other problem, but then even B can be solved in polynomial time, it doesn't mean that A can be solved in polynomial time. So we require this transformation to be done in polynomial time. So let me give you an example here. So the first problem that we are saying here, clique in English, it means that a small group of people that know each other very well. So in graph algorithm, so what does clique problem do? Okay, so we are given an input graph, which is undirected. Okay, and then we are also given an integer k. We want to find out whether there are k vertices inside the graph that are connected to each other fully. So in that sense, we are asking whether the graph contains a complete graph with k vertices, or at least k vertices. So either the answer is yes, we can find a group of k vertices such that they are really connecting to each other, or no, when the graph doesn't have such kind of k vertices found. So this problem is an NP problem. It is because if it is a yes, and if the input gives us a yes as the answer, then we can really tell what are the k vertices as the proof. So this problem is in NP, and this problem is also known to be NP complete. Now let us take a look of another problem called independent set. So independent set asks about the opposite thing. So we are given a graph G and an integer k. This time we ask the opposite. Can we find k vertices such that between them there is no edge? So can we find k isolated vertices in the graph? So they can connect to other vertices, that's okay. But within these k vertices, they do not have any edges between them. So this is an independent set problem. And obviously, independent set is also in NP. The reason is that we can give a very short proof, the k vertices as a proof, so that people can verify whether there are no edges between them in polynomial time. So this problem is polynomial time verifiable. Okay, so both problems are in NP, and then we know that clique is NP complete. So can we use the transformation idea or the reduction idea to show that independent set is also NP complete? Now, when we make transformation, we really need to make sure our logic is correct. Okay, this time we know that clique is hard, but then we want to show that independent set is as hard. So we want to establish the fact that if we can solve independent set, then we can solve clique. So we want to transform clique into an independent set problem. So how do we do so? That's easy. Very, very easy. So you have a graph G. I want to find the k vertices that are connected to each other. I don't know how to do so, but let's say there is a friend who always can tell whether we can find k vertices in the graph that are not connected to each other. So how do we do so? How do we make use of our friend here to help us solve the original problem? One is about k vertices connected to each other, and then here it is k vertices completely not connected to each other. So what we can do here is that we are given a graph G, we construct another graph. Okay, this graph is the complement graph of G, so that in the new graph, whenever there is an edge of G, there will be no edge. Whenever there is no edge in G, there will be an edge. So we construct a complement graph of G, and then give our friend this complement graph. So whenever our friend gives us a solution, oh, it says yes, okay, then we know that the k vertices in the complement graph, they are not connected to each other. So that in the original graph, they must be connected to each other. Okay, on the other hand, if our friend says no, there is no way to find k vertices in the complement graph that are not connected to each other, then we can be sure that in the original graph, there is no complete graph of size k. Yeah, because otherwise, there is a contradiction. So what do we know? We know that whenever we have a graph G for click, we can turn it into a graph G prime for independent set. The turning, the transformation, or the reduction takes polynomial time because we just replace an edge with the not an edge and not an edge with an edge. So if a graph has n vertices, it runs in order n squared time to complete the reduction process. And after that, then we have also shown that whenever we know how to solve independent set, we know how to solve click. So in such a case, independent set is NP complete as well. Okay, so yeah, this is all about the NP hardness that I want to show. So this may not be easy. Okay, so first of all, this is very important. Make sure you understand that NP, the N there is not meaning not. The N there means it is non-deterministic guessing power. So the computer can guess the proof correctly, you can say. Yeah, because non-deterministic guessing power means that it can try out all the different kinds of uh, guesses simultaneously. So somehow one of them, if it is a yes solution, then if the solution is yes, then that means that one of the proof has to be correct and short, so that the guessing power will always find this out. Okay, so if you are okay with this already, then yeah, this is, I'm really happy. So the first thing here is we need to understand what is meaning by NP. So non-deterministic guessing power plus polynomial time checking method. Okay, so this is NP. And then we also want to, so to summarize, the other thing that I want you to know is what is meant by NP complete problem. It is the hardest problem in NP. And then the third thing here is that what is the problem reduction technique? So how can we prove that a new problem is NP complete? So one technique is we have an established NP complete problem, and then we want to show that we can always transform this NP complete problem into a new problem, so that in polynomial time, so that we show that the new problem is also NP complete. Yeah, I think that's all for today. Yeah, thanks for coming. Yeah, thanks so much for coming, and then see you on Friday. We will have a homework solution for homework 5 and homework 6. Okay. So bye for now. Okay. Thanks.